things we learned last week. And last week we're talking about acids and bases. And so let's review our definition of an acid. An acid, we said, really is something that kind of produces H plus ions. Okay, so we produce if a substance, when we put it in water, it breaks down, it ionizes, and it produces H plus ions. In other words, it's producing hydrogen cations, right? So let's see how that would look in a formula. That would be forming an acid, right? So we put, let's say, hydrogen chloride, which is hydrochloric acid, and we put it in water, and then it breaks up, it ionizes, and we have H plus water plus chlorine. Okay, so it's floating around there. And then what happens as it breaks up, the H plus, because it's so incredibly grabby, it's grabbing to fulfill its outer shell of valence electrons. It'll grab the water, and this then goes to like step 2, and we have H3O, and it's still got an extra, it's lost it actually has lost an electron, so it's a positive charge, plus we've got chlorine floating in the water. So this water plus the hydrogen ion forms a hydronium ion. So oftentimes you'll hear that an acid forms hydronium ions, and there you have one. Now you know why they say that. The hydrogen just combines with water and forms that hydronium. Okay, now, and so the other thing often is that you'll hear it's a proton donor. Okay, an acid is a proton donor. It produces hydronium ions, and it produces because it produces there, it's a proton donor. Okay, it comes up with protons. It gives them away. It produces these protons. So it's a proton donor. Okay, a donor is something that gives something to another. So it's giving up what? Protons. It's giving up protons. It's producing protons, and so it's making hydronium ions. Hydronium ions as well. Now, let's look at the now that's the Arrhenius we mentioned last week. That's the Arrhenius definition. This is the classical chemistry definition of what an acid is. It's a proton donor. Okay, but let's take a look at what actually, let me clarify that. The Arrhenius definition says that it's producing hydronium, H ions, and therefore it makes hydroniums. Okay, that's what the Arrhenius definition was. But there's another two scientists, Bronsted-Lowry, and their definition of the acid is that it is a proton donor. Okay, so you have two kind of definitions there. You can understand how they're connected. It all has to do with when the acid goes into liquid, it ionizes, and the H plus ion grabs the water and produces hydronium ions. Okay, that's really what an acid is. So first Arrhenius posed this, but then Bronsted-Lowry also came in and said, yeah, it's a donor. It's a donor of hydrogen ions. Well, let's look at what a base is and review that definition. A base is kind of opposite from an acid. It would be any substance that when you put it in water, it ionizes, it breaks up, goes into ions, and produces not hydronium ions, but OH minus ions. And they call these hydroxide. You guys know that. These are hydroxide ions. So the Arrhenius definition of a base is any substance that produces what? Hydroxide ions. Okay, when it ionizes in water. Now, if you look at the Bronsted-Lowry definition, it's tied to that. It's close. And they are talking about there that when this is dissolved in water, it is producing the OH ions. And the OH ions are floating freely through the solution as well. Okay, so these OH ions are produced. So this would be, according to Bronsted-Lowry, when you produce OH minus, you are actually saying this is a base, it is a proton acceptor. This base is a proton acceptor. Okay, so as this OH floats around in the water, and it's going to grab H's that are ionized, and it's going to accept those H's. It's a base. Okay, and so it's a proton acceptor. So now what happens, and let me just show you maybe let me give you a real good example of that. Let's take ammonia, and here's ammonium, NH3, and we're going to put it in water and let it ionize, break down. It's going to produce, it's going to accept an H from the water. Remember, the water breaks, ionizes as well. And so we have NH3, and it's going to accept a hydrogen from the water, okay? And then as the water breaks up, there's going to be an OH minus and a hydrogen, okay? So in the second step, this is the first step, the water breaks down. In the second step, the NH3 plus the H forms NH4 plus, there's the ammonium, and you have OH minus, okay? And so you've produced OHs, but you've made this a proton acceptor, okay? So because this has become a proton acceptor, it's a base, okay? So the bases are different. They can be caustic, they can burn just like an acid can burn, because these ions are trying to combine with other other atoms to make a molecule. So that's kind of what we learned last week. A little bit of a review. Now, when you produce, and an acid produces H3O ions in water, the hydronium ions, okay, the more of these ions that are produced, the stronger the acid. So the less ions produced, these H3O, these hydronium ions, the less ions that are produced means it's a weaker acid. So it just depends, the strength of the acid depends on how many of these ions are produced when the acid ionizes in water. Now, when we look at something like HCl, hydrochloric acid, when it goes into water, it breaks up, it ionizes, and it produces H plus and Cl minus. Okay, I think we can understand that. But there's water that is also molecules of water that it's in, and so there's a second reaction, and the H2O and the H plus form H3O plus. There's your hydronium ion plus chlorine that floats in the water as an ion. Now notice that this HCl produces one hydrogen. There's one hydrogen that's going to come loose here as it breaks out. So this is called a mono, meaning one, protic acid. It's a monoprotic acid. The most that will come loose, the most hydrogens that will come loose is just one hydrogen off each molecule. Let's take another acid like H2SO4. This is sulfuric acid. And sulfuric acid will break down and you'll have H plus another H plus SO4 minus plus the water that it's in, you see. And notice what you get. You get two of these hydrogens that are breaking down. Now, in this case, sulfuric acid can produce two. So it's called a diprotic acid. And you might think, well, gee, that's got to be a stronger acid because the potential is for more of these H3O plus these hydroniums to be produced. And that's true in that regard. There is more opportunity. But in this case, this particular acid, I made a mistake. Oh, I didn't. This has got two minuses here. In this particular case, fewer of these hydrogens actually form the hydronium. So this is a weaker acid. It's not as strong as hydrochloric, okay? That's just the way it reacts. That's the way it does. I think part of the reason that these H's that have ionized here don't form is that the SO4, the sulfate ion, kind of prevents them. As it's floating around, it kind of blocks them from making as many hydroniums. So it's a weaker acid. So the less hydroniums that are being made show that it's a weaker acid. Now, we also have an example of an H3PO4, and you remember the phosphate ion has three negatives, right? So you're going to need three H positives. Each one is a +1, right? Each hydrogen has a +1, and so they balance. Remember that? So they're going to balance out to be 0. And you have just H3PO4. And that's what the phosphoric acid, I'll go ahead and write that, phosphoric acid. So this would be an example where when it goes into water, it ionizes, and what does it have? It's got a potential of 3 hydrogens, right? It's got an H plus an H plus an H plus PO4 minus, 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 that are all in water. So because it has a potential of 3, it's not a monoprotic, it's not a diprotic. What would it be? You got it. Absolutely. I could hear Miss Mason just shout that out just now. Triprotic. Very good. Oops. See if I can spell here. Triprotic. Excellent job, Renee. Good job. So this is a triprotic. And so now that's a little new stuff there about naming some of these acids in terms of their potential to ionize, right? But let's now look at some of the bases. And a base, remember, is producing OH minus, the hydroxide ions, right? So let's take 3 bases. Calcium hydroxide. What is this one? Potassium hydroxide, right? And what's this? Yes, sodium hydroxide. All 3 of these, all will readily dissolve in water. They'll ionize, they'll break up in water. And so all 3 will dissolve in water and they will yield a metal ion and an OH ion. Remember that? The hydroxide. Right, let's put a little minus there because it's always a minus ion. Okay, so as an example, NaOH will go into water and it will dissolve into Na plus, and it's in water, so we'll just say aqueous, and it will also go into OH minus, also aqueous, AQ. We use a little Latin term there, aqueous, aqua. Okay, so this would be a base. This is a base, okay? And we would actually use a substance called litmus paper. And we do a litmus test. Sometimes you'll hear that kind of just used as any old test that will determine if something is acidic or basic. Well, this is a base. It's producing OH minuses, okay, hydroxide ions, and the litmus paper will turn blue or pink depending on the amount of acid or base. So that's what you use to check out if something is basic or acidic. And you've probably seen people do that for swimming pools. You know, they'll look at a swimming pool and they'll put little droplets. Well, they used to put litmus paper in there, and they see how the litmus paper turned. Because if a swimming pool, let's say it gets real acidic, that can really burn your eyes, as an example. So you want it to be more neutral. So you aim for a neutral charge. If it gets too acidic, you put in some base and you kind of balance it. Okay, you neutralize the acid. Okay, so you want to neutralize the acid. You need acid in there to kill the bacteria, and you need to kill the growth of algae, but you don't want it so acidic that it hurts your eyes. So you have to neutralize the acid with a base. So generally speaking, bases and acids can neutralize. So before we take our break here and move to the next frame, the next part, I'd like you to look up page 253. And there on 253, we're looking at the hydronium ion concentration. The hydronium ion concentration. And there's a term for that. It's called pH. pH. So we say, what is the pH of the water? Or what is the pH of this food that I'm eating? And it's really measuring the hydronium ion concentration. And as you can tell from the chart, less than, if the pH, which is the hydronium ion concentration, if it's less than 7, it's acidic. If it's more than 7, it is basic. We would say it's basic. Okay, so we have those two extremes. So you need to be familiar with that chart, not memorize it, but you should be familiar. You should know, for instance, on 253, I want you to turn with me at this point, and you look at that chart, you should know, for instance, neutral would be pure water, blood, and eggs. That makes sense. Your blood needs to be neutral, needs to be at 7. Pure water is 7. But look how, as you go up the chart, and the pH goes down, okay, when we go down from 7 to 5, there's coffee. So coffee is pretty acidic. You know, that's why people that drink a lot of coffee could have ulcers or could burn, but it's fairly mild. Look, another 10 times the acidity as you go from 5 to 4 are tomatoes. So a tomato is 10 times the acidity of coffee. Well, tomatoes are good and grapes are good, but then you get into 10 times that is soft drinks and vinegar. Well, if you put a lot of vinegar or soft drinks on your teeth, you're going to get some cavities. So you have to be careful with those. And then look at lemon juice. Same thing with lemons. You know, a person that sucks on lemons a lot, that could be very damaging to your teeth. And then you get way up to pH of 1. There's your stomach acid and concentrated HCl. So the acidity goes up, stronger acids as the pH goes down. And then as the pH goes up, you get less and less acid and more base. So look at the bottom part of that and be familiar with soaps and lye soap. Look at lye way out the bottom. See, lye, 14, pH of 14 will burn you just as bad as pH of 1 at the opposite end, because it is forming an ion that will grab try to combine and will damage those tissues. So be familiar with those relative amounts of and relative pH values. Let's go to part 3.